Question. Do you prefer interruptions in the middle, or would you like the questions at the end?
Interruptions in the middle are fine.
Okay, perfect.
So yeah, I'm going to tell you all about the work that I've been doing at Texas A&M, working with these massive quiescent galaxies with this Hubble Grism data. Can you all see my screen?
Yep.
Okay, good. All right. So the first thing I'm going to talk about is the CLEAR survey. This is where I'm getting all my data from. Then I'll talk about some of the issues of working with Grism data and how I try to circumvent those. I'm going to briefly touch on my 2019 paper, which is about fading stellar populations of massive quiescent galaxies. And then I'm going to focus more on my more recent paper, which is all about the connection between formation history and morphology. So first of all, CLEAR. This stands for CANDELS Lyman alpha emission at reionization. This is a deep G102, which is the bluer of the two with C3 Grisms. It's a fairly deep Grism survey of goods north and goods south. And this is, we chose, goods is a really good field to do this on because there's a ton of photometric data. There's a ton of, there's G1 for 1 data as well from 3 HST. So there's a lot of data here that we can use to fit the stellar populations of these galaxies. So if you've never seen Grism data, here's an example. On the left, you have the direct image, and I've highlighted some objects here so you can sort of see what happens to them. On the right is the Grismed image. And you can see that it sort of just like smears out all the light. And Grism data is great because you get a ton of spectra. I think in this image alone, there's over 400 spectra. So you can get a ton of data. It is low resolution. The G102 Grisms are of 200, G1 for 1s are of 100, but you do get a lot of it. But one of the big downsides to Grism data is that you're getting spectra for everything, and it's a mess. You can see in this image on the right, we have to worry about 0th order dispersions. There's just objects falling on top of each other. So it is a fairly contaminated image. But luckily, there's a lot of smart people out there and they've thought of ways to get around this. And so the way we do it is to basically just take Hubble and turn it, dispersing the light in a different direction. And so here's an example of why this is important. In the top, this galaxy here in the center, this is our object of interest. And just to the right of it, there's a contaminating source. And if this was the angle you use to disperse the light in, the two spectra fall on top of each other and there's really no way to remove them. And so that spectra is just contaminated. But by turning Hubble, you can begin to separate the two spectra. You can see that contaminating source, its Grism spectra is slightly higher. And by doing this, we can better model this contaminating source and remove it from the spectra. The other big issue with Grism data is morphological broadening. And so what this is basically what the Grism's doing when it creates the spectra is it's taking the image of the galaxy and stamping it down at every wavelength. And so the larger the galaxy is, that more of that light from different wavelengths will bleed into the others, effectively smoothing out the spectra. So in this example here, I have two galaxies and I've given them the same ACD, but you can see the difference between this compact source and the extended source. And so Grism works really well for compact objects. You're going to get the best use out of it. For the more extended sources, you do start to blend lines, you to start to smooth things over. This is an exaggerated example, but this is, this just gives you an idea of what this morphological broadening can do. And it gets more complicated, right? Because it depends on the galaxy's shape and the orientation of Hubble. And I just stated that we have to put Hubble in different orientations to disperse, to remove the contamination. So you have to deal with this at every pointing for every object sort of uniquely. So the way that I've done that is to use this Grizzly program developed by Gabe Brammer to do this forward modeling technique. So Grizzly is just it's this Python package that does everything you want for Grism data. It'll extract out all the spectra, create a lot of nice data products, and it'll also do the forward modeling. And so the way this works is I take my models, I'm using FSPS, you redshift them out, you convolve them with this, the morphology of the galaxy at the right angle, and then it'll create this simulated 2D Grism spectra. And then you can, everything that I'm doing up to this point has been in 1D, so then I extract that down to 1D. And this is the actual sort of model spectra that I would be fitting to my objects. And so the redshift range that I'm interested in is between 0.7 and 2.7. And the reason for that is because in the two Grisms, the G102 and the G141, which are shown here, the G102 wavelength coverage is in blue, G141 is in red. At these redshifts, many optical age and metallicity features are going through the Grisms at this point. Things like the 4,000 angstrom break, Balmer lines, several other metallicity features. And so this is the best, we want to fit ultimately the stellar populations, ages, the metallicities, things like that. And so we'll get the best fits using this redshift range for these two Grisms. Now, the first thing I'm going to talk about, I'm going to briefly talk about my 2019 paper. We actually limited ourselves in that paper to only using the G102 Grism data from CLEAR. And I said earlier, we're in good, so we have a ton of photometric data. We have the 3D HST G141 data. But here we're limiting ourselves to just the G102 for several reasons. One, we wanted to see if you only had a Grism spectra, how well could you actually, can you actually constrain stellar populations? And if so, how well could you do this? And the reason for that is because, with James Webb and the Roman Space Telescope going up soon, they're going to produce a lot of Grism spectra for objects that may not have any supporting photometric data or anything else. So the only thing you may have for that galaxy is Grism spectra. So we wanted to see if just given a single Grism spectra, how well could you actually constrain these things? And that's why we had to limit ourselves to a redshift range of 1 to 1.8, because in this range, this is where the G102 is actually covering these age and metallicity features. And the galaxies that I'm interested in are massive quiescent galaxies. This is an actual Grism spectra for one of my galaxies. In blue is the G102 Grism spectra. In red is the median fit model. On the right, you have the 2D likelihood for metallicity and age. You can see the age metallicity degeneracy right there. And on right here, we have the age posterior and the metallicity posterior. And we found that we could constrain these two properties fairly well. These are sort of typical fits for our galaxies. So yeah, the main result from this paper, I think, was our metallicity. And what we found was that the mass and stellar metallicity relationship showed no evolution in redshift. Our results matched that of results from lower redshift from Anna Galaxies work, redshifts of 0.1, 0.7. She found that these massive quiescent galaxies basically had stellar solar metallicity, stellar solar metallicities. And that's what we found. We found the exact same thing. We had basically solar metallicities for this sample. And this is really interesting because, there's no evolution in this relationship, at least up to the redshifts that we're probing, but the mass nebular metallicity relationship does evolve with redshifts. So this begins to introduce questions of sort of, is this solar metallicity a prerequisite for galaxies? Is this somehow linked to the quenching? yeah, it just brings a lot of interesting questions. And definitely something we're going to look more into. But so that was the first one, and it sort of proved that we could do this with the Grism data. Just using the Grism data, we can extract the stellar population. So we wanted to push this further and effectively, take the handcuffs off. So now, moving forward, all of my work has been using the full data set for these galaxies, the photometry, the G141, Grism, Spectra, and fitting all of those simultaneously. We made some additional updates to the fitting routines, some minor ones and some major ones. Some of the more major ones are now, we're fitting using non-parametric, and I'll make sure to do the air quotes, non-parametric star formation histories from Joe Leja's work. We're also using Dynasty to do our fitting, which is this nested sampling algorithm. Just does a really nice job of doing the fitting for us. And so here's a comparison on the right. It's the same galaxy. On the bottom, G102 Grism Spectra is in blue again, but now we have the photometry and the G141 Grism Spectra in red. And we applied over that a best fit model, and you can see how well we can constrain these galaxies, their stellar populations. But I think the more interesting thing is to the right of that. So in black are all the constraints from above. So just using G102. And in red are the constraints from this more updated fitting method. And you can see, first of all, we are consistent, which is good. We want to get similar results. But we can constrain these properties a lot better. Much, much tighter constraints for both metallicity and age. And one of the biggest differences is that I'm not just going to be focusing on massive quiescent galaxies. I'm going to be focusing on all massive galaxies. Redshift range, again, 0.7 to 2.7. And this leads to about a sample of about 1,000 massive galaxies. And massive here is just anything above 10 to the 10 solar masses. And I've had some interesting examples. So on the top left, I have a star-forming galaxy. Obviously, this thing has emission lines, and I'm not fitting to the emission lines. So currently masking out anywhere there's an emission line. But you can see we can recover the continuum, fairly well. To the top right, something, maybe this is more like a post-starburst galaxy. It's got some deep Balmer absorption, H-alpha emission. And then we got more typical quiescent galaxies, similar to the things I was fitting in my first paper. So what actually happened is, so the first thing I fit when I was doing this, a sample of 1,000 galaxies, is I fit to the massive quiescent stuff, because this is the stuff I'm more used to fitting. They're a lot easier to fit. And once those results came in, we took a look at them and saw a pretty interesting relationship. So we decided to then publish the second paper. Actually, when I published my second paper, I wasn't actually done fitting all these galaxies. It was just like, wow, this is really interesting. Let's get this result out. And what we saw was really motivated by work from Sarah Wellens. So she took a look at some massive galaxies at Redshift 2 and Illustris. And she was trying to answer the question of how do you form a compact galaxy? And so she describes two primary tracks. The first is this early formation track. Essentially, galaxy forms in the early universe when everything was more dense. So this is where the galaxies get its compact morphology from. The other track she describes is starburst track. So something happens, maybe major merger, something like that, causes a massive amount of stars to form, sink towards the center, and that's what creates a compact object. Now, what she found here, so we have formation redshift and the effective radius, which is she's going to use as the measurement of compactness. What she found was that as you go towards the more compact galaxies, the cell formation redshifts went to higher redshift. That's pretty interesting. So this is, these galaxies here have the earlier formation tracks. So we thought, well, we have this large sample of compact quiescent galaxies. Let's, we have these more updated star formation histories. Let's see what we find. To do this, we selected the sample using a UBJ diagram for our sample of quiescent galaxies, and we found around 100 from our entire sample. And here are some example fits. So, the fits to the data here, the morphologies to the left, and on the bottom is star formation histories. Now I mentioned I was using Joe Lage's star formation histories. The way that these work is you take your period of star formation and you cut that up into several time bins. I chose 10. You can choose however many you want. And then you're essentially just fitting for the amount of mass formed in each bin. And here are all the different sorts of shapes we get. We have galaxies like this galaxy right here, which wanted to basically form all of its mass before a redshift of 4 and then suddenly quench. Galaxies like this, which have a more steady star formation and then a sudden quenching. Galaxies like this, which, again, more steady and a more steady decline. We have galaxies like this on the right, which, we're not sure what this bump here is. Maybe it's a burst of star formation, maybe it's rejuvenation, we really don't know. But we can get all sorts of shapes using these star formation histories. But the thing we're the most interested in from these star formation histories is a formation redshift. This is here marked as a vertical red line, and the green region around it is the confidence interval. So this is T50, or the look back time to when this galaxy formed half its mass, or Z50 in redshift space. And the thing we're the most interested in is Z50, its formation redshift. One of the things we wanted to see is what's driving our fits to the star formation histories. What in the data is driving these fits? So to figure this out, we took a sample of our galaxies, specifically galaxies from redshifts of 0.9 to 1.1. We split them into two groups: early forming galaxies and later forming galaxies. We took a ratio, we take those two groups, we stack their Grism spectra and photometry, then we took a ratio of the later forming galaxies to the earlier forming galaxies. And what we found was that, well, in the photometry, we see a lot of excess UV flux in the later forming galaxies, and that makes sense, right? These galaxies formed later, they have more recent star formation, so you should see an excess in the UV. We see something similar in the Grism data, as well as evidence of deeper Balmer absorption. So these are the properties that are really driving the fits to our star formation histories. And so now we need a measurement of compactness. Here's my size mass relationship for these galaxies, which the galaxies are here in these colored points. And I'm using sigma 1. And the way that we derive sigma 1 is pretty straightforward. We're using measurements from Vanderbilt 2014. We're going to take the Sursic profile, integrate it out to 1 kiloparsec, integrate it out to infinity, take the ratio. That's essentially going to be sigma 1. And so going back to the size mass relationship, the points here are going to be scaled by sigma 1 such that the smaller points have higher sigma 1 values. They're more compact. And so the compact galaxies lie basically where we expect them to lie, at the edge of the size mass relation. But there is a good bit of mixing of some of these less compact galaxies with the more compact galaxies, which is an interesting consequence of using something like sigma 1. And so what we found was that, and this is going to be formation redshift and sigma 1, or compactness, essentially. What we found was that as we go towards the more compact side, the most compact galaxies, they all had higher formation redshifts, such that none of the most compact galaxies had formation redshifts lower than a redshift of 2.9. And then there's almost this envelope that forms. And in fact, if we were to take this relationship and smooth it over, we find that the formation redshift and compactness rise monotonically with each other, and the standard deviation falls. Now, similar work has been done looking at formation redshift and stellar mass. And so when we look at that, we see something similar. As you go towards more massive galaxies, they have higher formation redshifts. And one of the questions I get all the time is, all right, great, which one's more important in relation to the formation redshift? Is it sigma 1 or is it stellar mass? And at this point, we really can't say, because those two quantities are, they're highly correlated. So separating that out is at this point probably not doable. But sort of by eye, it appears that the sigma 1 value is more important. Stellar mass seems to have this turnover in the slope, but we just need more galaxies to be able to say anything sort of certainly. But so great, there's this relationship between formation redshift and compactness. Then why are there these galaxies that have more extended profiles that also have earlier formation times? So to figure this out, I took the star formation histories of the early forming galaxies. Early forming galaxies are galaxies that have formation redshifts above redshift 2.9. And I take those and I stack star formation histories as a function of redshift, as a function of sigma 1. And here's what we find. So these are the stacked star formation histories. They're colored such that the lighter are the more extended star formation histories, and the darker are for the more compact galaxies. And we see that there's a difference in the shapes of the star formation histories. And I'll just point out that this plot is not normalized, right? But you can see, especially at sort of the later end of the star formation history, that the shape is just different. In fact, you can see that more when we look at these sort of cumulative star formation histories. There's almost a gradient that forms, right? And such that the more compact galaxies are forming their stars quicker. Or another way to say that is more extended galaxies have more extended star formation history. To quantify that, we took the quenching timescale, which we're just going to define as being T50 minus T90. So the time from forming half your mass to forming 90% of the mass. And what we see is that the quenching timescale is correlated with compactness, such that, again, the more extended galaxies have more extended star formation histories. So, going back to this plot, we wanted to figure out, is there some sort of mechanism then that can cause galaxies to have extended profiles and extended star formation histories? So if you just assume that all galaxies that form at early times, any galaxy with an early formation, if it formed compact, it would have formed here. Is there some mechanism that can then cause it to drift in this direction, extend its profile, but not change its formation redshift by much? So we looked at several mechanisms, and it turns out that minor mergers are probably the best candidate. So we looked at these from Rachel Bezanson's work, and in there she says that, yeah, many minor mergers can, in fact, cause the profile of the galaxy to extend. So you can change sigma 1 with many minor mergers. And these minor systems are more likely to be star forming, right? So they're going to have more recent star formation. And if the resulting star formation history from these two are just sort of summing the two star formation histories, well, you're adding a lot of the star formation at the end of the star formation history and effectively extending it out. We looked at this using a pretty simple toy model here, just taking some delayed tau star formation histories. And what we found was that, yeah, minor mergers can change the quenching time scale by a large amount when things like minor mergers couldn't. But also importantly is that it didn't change the T50 value, right? Or which is related to Z50. It didn't change that by much. So this is saying that minor mergers can do both. And so going back to this and going back to Sarah's paper, where she defines these two paths to form compact galaxies, what this is sort of saying is that the most compact galaxies here follow that early formation path, right? They get their compact morphologies from having formed in the early universe. And the reason I say that is because, well, starbursts can happen at any redshift. And so if starbursts are responsible for the most compact galaxies, then we should see them at lower redshift, and we simply don't. So then the likely story here is that these galaxies, these early forming galaxies they formed compact, sort of formed in this bubble here. Over time, some of these went through many minor mergers, extending their profiles, extending their star formation histories. I'm going to skip over this last bit just because of the time and get to my summary. So just to summarize my work, I've been looking at these massive galaxies using Grism data. And some of the main results have been that we find no evolution in the mass stellar metallicity relationship, at least at the redshift of 1.8. This is something we're going to continue to probe all the way to redshift of 2.7. And we find this relationship between formation redshift and the stellar mass surface density. And this is something, again, we're going to continue to probe this. And in fact, here are some updated results. In red are the quiescent galaxies, which is the population I just looked at. In blue are star-forming galaxies. And we see that this relationship, this envelope that seemingly forms, continues on down to more extended galaxies. This is something that will be coming out in a later paper, but this definitely is really interesting results. So yeah, thanks, and I'll take any questions.
This was awesome. Thank you so much. Remote Zoom applause. All right, so let's do questions. Would anyone like to go first?
Can I?
Yeah, absolutely.
Coming here. Lovely work. Thank you so much for this presentation. It's really nice. Maybe I missed it and you said it, but I'm not sure I understand. I'm looking at your plot with the star formation histories and where you see a gradient and the difference in the shape of the star formation histories with more or less compact galaxies. Yes, that one. Yeah. Yes. How much of it is really the galaxies being more or less compact, and how much of it is the galaxies being massive or less massive? Because I see, well, it's a clear trend also in mass here, because the least massive are the yellowish ones, right? The most massive are the black ones. Yeah. Do you have a sense of how much of it is contributed by them being compact and how much just massive?
Yeah, that is difficult to say. I did not repeat this same exercise for just doing this by mass instead of stellar mass surface density. I would think you would see something similar because, again, these two quantities are highly correlated. I don't know if it would be as nice of a gradient as this. I mean, that's something definitely going to look at in future work.
So you could take out the mean trend of mass with compactness or sigma 1 with mass, right? And just look at the residual on the mean trend and see whether, if you're high on that residual, are you formed earlier? And if you're low, are you formed later?
Yeah,
sorry, with the idea I was trying to understand is basically, if you look at the color coding Vince has, which is sigma 1 for the left-hand plot, and just kind of bin them up, and then not bin them up, but take the median in mass.
So you're instead of your sigma 1 being color coded by sigma 1, it's color coded by the difference in sigma 1 relative to the mean for that mass.
Yeah, that's an interesting question. Right. I don't think we looked at that. We didn't look at that. If there's some, if there's a third axis on this plot, what is the residual about that fundamental plane or something, right?
Yep, exactly.
Yeah. That's cute. That'd be neat. That could be interesting to see.
On a slightly related note, although not the same, if you look at like just the full CANDELS sample, using Jehan Katar-Tepe's visual classification catalog, like there you see a similar trend for objects classified as compact have much sharper, shorter star formation histories than the general sample. The problem is that most of those classifications also have like the flag that says that this classification cannot be trusted. So the result isn't as robust.
Hi, Vince. I have a question on the same plot here. So when you're mentioning this, you also brought in the starburst phrase in trying to explain this whole scenario. So in that context, I have a small question. So simulations by Jorge Moreno, Jeremy Finch, and so on of major mergers at high redshift suggest that major mergers don't actually like enhance the ongoing star formation at these high redshifts, like above the mean value that's already happening. So I'm trying to comprehend. So since you're showing that at, these compact galaxies at high that have higher star formation, higher formation redshifts, like have these sort of sharp burst and sort of fall off situation happening. And I know you are invoking the major merger and minor merger scenarios into this picture. So I'm trying to piece together the predictions of high redshift galaxy mergers not actually enhancing the star formation to a starbursty phase, and this scenario right here. Like, what's your comment on that? If that was the scenario.
So if you had, you're saying if you had starburst at early times?
Right. So essentially what simulations are saying is that galaxies are already forming at a high rate at those redshifts, and major mergers don't effectively enhance the already high star formation that's happening there. It's basically, they're saying that it's hard to create a starburst with a major merger at high redshifts, at 2 and so on. So since it's in the similar sort of redshift range at high redshifts, and also formation times of z greater than 3, like how do we comprehend such a scenario where major mergers are not actually enhancing the star formation, and how would then, if that's the case, what is causing the compaction?
That's a really interesting question. I think like what we're saying is that they're getting, these galaxies are compact because they formed at early times and just in dense, halos. And so that's what's causing them. They're not getting more compact over time, where they sort of, they grow up all their mass and then, whatever. I'm not sure what we could do about this major merger. I mean, it's totally possible that, if a galaxy over here, you had to have some sort of major merger event, but I don't know that our star formation histories can say anything about that.
They're disfavored in your prior on the star formation, right? Because you have this continuity prior imposed. So they're disfavored. It's not to say that you can't have a recent burst, but it would have to overcome the prior.
Yeah.
But it is an interesting question. I mean, one thing, we didn't have to see this trend. If all galaxies became compact in sigma 1, as Vince was saying, because they experienced a recent merger, which, compactifies the galaxy, then you would expect there to be young, so recently formed in Z50, high sigma 1 objects. And that's just what we did. Those are few and far between. So we can't say they don't exist. I think all we can say is that the compact objects we observe at redshift of 1 to 2 now all favor these very early formation redshifts. Right, so they downweight, sorry, something in my throat. But they would disfavor kind of one of those, at least a compaction event that ends up with a young stellar population in the core. I think that's something we disfavor, right? Yeah. They can still happen, they just can't get to like above 10 to 10.2 in sigma 1, right? Would you agree, Vince? I mean, that's kind of how.
Yeah, well, if you look at this plot, we have, because one of the things I was wondering was like, what about compact star forming galaxies? Could they have these later formation times? And when I look at all the galaxies in clear, none of them, fall below this sort of ridge. Even star-forming galaxies in this population, these compact star-forming galaxies have early formation times, sort of in line with.
Right. In fact, you see a few objects over there, right? They're relatively younger Z50 objects at 10 to the 10.0 or something.
Yeah.
So maybe those are the ones that are more recent, compaction type events. But yeah, but the trend still holds, which I think is really interesting. And then, with this group, I'll ask the question, what systematic could be correlating these two axes? Right, Vince and I were worried so much about that. I don't know, Vince, if you're going to talk about it or not. These people are a bunch of pundits. They might be able to think of some things we didn't.
Sure, yeah. So, one of the things we went over a bunch when we were writing this paper was, is there some systematic that's causing effect, these galaxies here for us to miss them? You couldn't think of anything because, if anything, these are going to be compact, more recent formation. We should see these. If they are in the sample, they should be there. There shouldn't be any reason that we would miss them.
So these were quiescent selected though, right?
The previous work, yes, not this work.
This one is not at all. It's just mass selected.
This is mass selected, yeah.
Yeah. Okay. Yep.
Now there's something similar happening at the high, there's this sort of bridge that also occurs, and this may be artificial because if you think about galaxies that formed at early times and have extended profiles, those might be easier to miss. We don't know, obviously, but that would be interesting.
Well, so I think of like ULERGs and submillimeter galaxies as the outliers in that they're massive and star forming. And so they would disappear from your plot because they're probably faint in the optical UV. So that's one bias. I don't know that it's a big bias because they're not thought to be big proportion of the numbers.
I mean, so Vince, it sounded like you were thinking about selection effects.
Yeah.
You used the word systematics, and I think that's important to also think about. So even if your sample is fairly selected, could there be systematics in how the photometry is done that artificially redden the most compact galaxies?
Yep, that was another one. I used the word systematic. Yeah.
And I doubt it's there, but I think that's something you could model relatively straightforwardly, just with fake object injection onto images and then T-fit or whatever the method is. And you're probably fine, but that would be a systematic to worry about.
Right, I agree. It has to be something that correlates.
I mean, if you took the same amount of dust and just made the galaxy more compact, if it's a well-mixed model, I have a feeling it gets redder. I don't know, but you would think that the chances of scattering off a dust particle are higher if you're compact than if you're not.
I wanted to mention dust as well, but I was thinking that usually if dust is in the interpretation, I mean dust in the interpretation, if dust is not properly interpreted, usually is overshooted, which means that the star formation rate is also overshooted, which means that T50 would be younger, not older. So it would not be a reason to miss the massive low Z50, I think.
And I think we agree, Cami. So, here, I'll try to be devil's advocate, even though, this is all Vince's work here, but because you're right, and we've tried to come up with some kind of extreme situations, like what if it's so dusty in the core, somehow you miss that, and it flattens out your surface brightness profile, so it pushes sigma 1 down as well. I think that would be kind of contrived, but those are the kind of scenarios. We're trying to come up with a way to correlate the star formation history really with either the mass or the surface brightness profile, right? And nothing jumped out at us, but it's one of those questions. And you guys are all hinting at good things, saying them a little bit better than I think we consider them. But
So there's a result from the starbursty galaxies. I don't know how much it's held up, right? But from Heckman and Moirer of a maximum surface density of star formation that you can hit, right? And so you could, in principle, calculate, well, okay, if you hit that during your starburst and then just fade, what is your, and it doesn't quite translate into sigma 1 because that's a surface density instead of a, well, I guess maybe it does. Solar masses per cubic meter, yeah, maybe it does. So maybe there's a way to see what is the aging line on that maximal density of star formation. What does that look like relative to what you see here?
Yeah. Vince, I had a couple of questions about this conclusion slide. One, you mentioned non-parametric SFHs for future work. Are those the same prospector SFHs you showed us here or something different?
The next several papers I will be, well, because I use the prospector star formation series, yeah. In the future, I am looking at different, but that will be for future work.
Okay, I was just wondering, when you call it non-parametric, are you running it in a mode? Are they still bin star formation histories?
Yeah, they're still bin.
And does the number of bins adjust to the data?
No, the bins are all 10.
Okay, so that's parametric. It's highly flexible. Those are good star formation histories. But if you use a fixed number of bins, it's just a different kind of parameterization, piecewise constant.
Yeah. No, I agree with you.
yeah, no, now Vince has to be, he's like threading, you know, he's in a rock and a hard place here, because if he says all that, then people like Joe Lesia are gonna, you know, put him on a cross and crucify him. And if he doesn't say all that, then I agree with you, Eric.
No, I'm sorry. It's like standing up to Trump. We have to stand up to Joel.
Exactly. Right. So that's why Vince said he's using the quotation marks around non-parametric. Absolutely. My answer to that is, I think last time I gave a talk on this at an actual conference, I said they're called non-parametric models, but they have parameters. And then I moved on.
But so that's good. And Vince doesn't have to fight the battle for us. But I would just emphasize that they're highly flexible and they're really good.
Yeah, exactly. I agree with you. And Vince can test, you know, what happens if he varies the number of bins and, you know, yada yada. But it's still a parameter. I agree.
You can just call them fake parameters.
Yeah, it's right.
Well, there's a problem from the start, of course, in the stats literature, because non-parametric doesn't mean you don't have parameters. It just means the number of parameters is varying. So it's like bad from the start. The other question I had was about the lack of evolution in the mass stellar metallicity relation. I think that's a really impressive result. I think it was convincing in what you showed us. But then I started thinking, I know that SFR M star evolves. And I've read papers saying that there's a fundamental metallicity relation between SFR, M star, and metallicity that possibly evolves.
Gas phase.
I'm wondering if these are all consistent with each other, or if they look different when we view in different projections, and if you've thought about that.
Yes, I have. So for this more updated work, I do have like the stellar metallicities for the star formation, for star forming galaxies. We do see some evidence that the quiescent, that there is sort of this, you know, mass metallicity relationship in terms of star formation activity. So massive quiescent galaxies have higher stellar metallicities, while the star forming galaxies have lower metallicities, even with the same masses. But we still, for at least for the quiescent sample, don't see any evolution up to a redshift of 2.7. Even when we look at that high, we see no evolution. Now we are sort of using these stellar tracks. So, you know, something we would like to be able to do, which we just can't currently do, is to check for like alpha abundance and things like that. Because these galaxies, you know, especially the early forming galaxies are definitely alpha enhanced, or, you know, very likely alpha enhanced, but we just can't measure that right now.
Sure. I guess if you could tell me something like you've looked at the SFR, you know, the fundamental metallicity relation literature, And actually the stellar mass metallicity projection of those data is consistent with what you're finding for massive galaxies, then it's all consistent.
And yeah, I don't think we've done that. No.
Yeah, I'm not. So I think it's actually interesting, and you bring a good point. So the relation between mass metallicity and star formation rate is all gas phase metallicity. So I think we have an out there. The other thing that's just interesting is of the like Redshift 2 star forming population, things with solar metallicity are really rare. And I don't really know how to, I mean, like very rare. You go look at Moss stuff and they have, you know, a few objects are up there around solar metallicity. And that's in the gas phase, it's oxygen abundance. But here, you know, Vince is clearly favoring solarish metallicity. So there's some disconnect between the things that are forming stars that we see in the gas phase, or the metals we see in the gas phase, and what gets locked up into stars. That's part of it. The other aspect is, and Vince mentioned this, is the metallicities we see or he constrains is some weird combination of alpha plus iron peak elements, because you're looking at stellar populations. And those are all fixed to solar abundances. I think ideally we'd vary alpha over iron using some better set of stellar populations to do that. I'd love to see what the outcome of that. I think could we actually look, you know, detect alpha to iron variation in these, you know, we kind of expect them to be 0.3 dex or something higher in alpha over iron. So there could be an out somehow that way, right? Like the metallicities we're measuring are really like iron, because that does most of the opacity in the stellar atmospheres, and that might be solar, but then alpha to iron is higher than that. You know, I think this is a really interesting problem to be focusing on. I don't think anybody really has good predictions for it. So.
Yeah, and I hadn't really thought about it. You're absolutely right, of course, the difference between stellar metallicity and gas phase metallicity. But when you're doing SED fitting with star formation histories, you in theory are getting information on both the extant stellar metallicity and the gas phase metallicity when those stars had formed. You could sort of do a 4-dimensional analysis, or even ignore SFR and do a 3-dimensional analysis. It would be kind of neat.
Yeah, no, I agree. Yeah, I don't know. I mean, Cami, you've worked with like Bruce Walsh-Chalot models a lot. I know they have these options to do evolving metallicities, and that must include some yield. I mean, that's a whole nother set of parameters now that you think about it, right? Like you can either just say, okay, we're just going to use whatever prescription there is for the yield and production, or you just make those more and more parameters. It's a great thesis. I don't want to have to write it, but somebody should.
Yeah, I mean, Anna Galaxies worked on that, making an analytic evolution of the metallicity together with the star formation histories. I don't remember the details of how she did it though. I'm doing it as well, but I use the semi-analytical model, so I have this metallicity history built in. So I just pick a different metallicity at every time step.
Yeah, so it's a really interesting problem. So
I
kind of goes back to the
feeling
Tinsley
you
thing.
need
Sorry.
a lot higher signal to noise, higher resolution data to be able to make inroads on that.
I think you're right. You
To
need, like,
get
actual
it out,
Yeah.
to get it out, yes, but that doesn't mean that it shouldn't be in the prior.
Well, it should be in the prior probably, because
Yeah.
it's a more sensible prior than single metallicity.
I mean, even simply having the first stars metal poor and the last stars more metal rich, that's a heavy prior, and but it's realistic compared to having everything at the same metallicity.
You could put it in a sort of a, you know, non-parametric-ish way by saying, okay, you move in a locus through the age metallicity relation, and you just define that as a spline or something that goes from solar down to 0. And you know, you could do that with a very small number of parameters.
Yeah.
I had another question on one of your plots. When you showed the sort of spectrum, the low resolution spectrum broken down by age, that showed that there was more UV light coming from the ones with the younger T50.
This one.
That one, yeah.
Yes.
So I think that's a sort of a non-trivial result, in the sense that if you imagine that bursts aren't particularly correlated with star formation a gig year earlier or whatever, the far left there, which is below 2,500 angstroms, that's pretty young stars. That's not your gig-year-old stars. That's your few 100 million years old stars. And so why they necessarily care that your early formation was 5 gig years earlier rather than 3 gig years earlier, it's not obvious why that part of the spectrum should care that much.
So, sorry, Vince, if you want to go ahead, like.
No, I don't have an answer for that. That's really interesting.
So I had one quick possible explanation, which is the continuity prior that you're using.
Mm-hmm.
Essentially penalizes very sharp deviations in SFR from bin to bin.
Yes.
So what that's doing is when you essentially like drag the SFR down, it's going to like pull all the other bins with it, one way or the other. And so it ends up correlating star formation rates over long time scales. So if you have a recent quenching sort of behavior, it ends up influencing the overall shape of the star formation history as well. So to me, this is sort of the difference between a quiescent and a quenched galaxy, if that makes sense. Like if you have something that stopped forming stars recently, with the continuity prior, you'll get like the black kind of star formation history. And something that's quenched, something that just hasn't formed stars for a long time, it'll look more like the red one.
Right, although yes, right there, but the photometry, the fact that they're going up at the far UV, that's sort of independent of those two curves, I guess.
I mean, it's still like you select these galaxies and then you bin them to find the photometry, right? So if there's a lot of,
I guess so, yeah.
They could have been forming stars until recently.
Yeah.
And then just in the last bin, they have lower.
Yeah. Okay, given the way it's computed, that's probably right. Yeah.
The last star formation bin, you mean? Right. I mean, I understand. But the point is, if you have far UV flux, it's going to have to include some recent star formation, right, in the last bin. And then the continuity prior will increase the odds that there was star formation in the next to last bin.
Yeah.
Right.
So
okay. Yeah. No, I would agree with that. I mean, that makes sense. Right.
Yeah, I don't know if you can do it from the Grism. I mean, from maybe some combination of the photometry and Grism, it'd be interesting to see if there's any separation. You know, if you look at local ellipticals where you have an old population and then you may or may not have a young frosting of younger stars, there's basically a local minimum in the SED that's probably around 3,500 angstroms or something like that. And then it'll go up either because of old hot stars like the UV upturn stars or younger stars. But the amount it goes up is pretty sensitive to recent star formation. So you might be able to see whether you have a lot of spread in that UV relative to 4,000 angstroms or whether they're all in a tight relation.
Yeah, that's true. That's true.
So, I mean, the questions so far have been great. Since this went over time, we'll just keep Cammy's update of the paper for the next telecon. And if we're doing that, then I just wanted to quickly ask if there are any announcements or updates that anyone would like to say for this telecon. All right.
For me.
All right. So,
Vince.
sorry, Casey, what did you say?
Oh, great talk, Vince.
Yeah. Excellent.
Yep. If I know that people have to leave at 3ish, and that should be completely fine. If anyone has any other questions, you can either email Vince directly or put them on the Trello board and I can send it to him. I have put up all the questions asked so far on the Trello board so that we at least have a record of that. And Vince, this was great. Thank you so much.
Thanks. Yeah, thank you all for having me.
Yep. I have a ton of questions that I want to ask, but then I don't know too much over time.
Well, we should definitely talk, me and you.
Yep.
Yeah. Thanks. Yeah.
All right. Good.
All right, bye, everybody.
Bye.
We'll reconvene in 2 weeks.